So with this lesson, we're starting our next unit, which is all about atomic structure, theory, and properties of solids. We're picking right off up where we left off in grade 11 with atomic theory. So up to this point, you should be pretty familiar with most models of the atom up to the Bohr model of the atom. We did a little bit with electron configurations in grade 11, and we'll go over some of it again today and in the next lesson. Um, but make sure that you're familiar with how the model of the atom progressed. And now we're going to take it to another level and expand our knowledge on the quantum model of the atom. So up to this point, if we're thinking about the Bohr model of the atom, electrons were moving around in fixed orbits, so those circular paths, the circular paths could only hold a certain number of electrons. And we know that that's not the real true model of the atom that's accepted today. It's a good generic model for most people, but if you're scientists or chemists, you know that there's a lot more to it. So we're going to try not to think about the Bohr model of the atom anymore, and we want to go on and think about orbitals. So now what we're trying to think about is electrons behaving like waves. So electrons have some energy, they travel through space. When they travel through space, they travel as waves. And instead of being stuck on these two-dimensional orbits, now we're going to find them in three-dimensional volumes that have specific shapes and dimensions. And these are called orbitals. Every energy level that's there still exists, but it has specific types of numbers um, for each of these different orbitals. When we talk about the orbitals and the electrons occupy them, they're found in the orbitals, but only with a certain probability, and we'll come back to a little bit more about that later in the lesson. The orbitals are also broken down into subparts or different regions. So think about like a big neighborhood, and within the neighborhood there's different homes, different shapes and sizes of them. Same kind of idea here with the orbitals. So now when we think about energy levels and tying in these orbitals with them, this is the pattern for the first four energy levels. So our first energy level, which is the principal energy level, will only have one sublevel, one type of orbital in there, which is called the s orbital. Our second energy level has two parts to it, two sublevels, 2s and 2p. The third energy level will have three sublevels, 3s, 3p, and 3d. Sorry. The fourth energy level has four sublevels, 4s, 4p, 4d, and 4f. After the first four energy levels, the pattern doesn't follow. There's not five in the fifth energy level. Um, but for the first four, it's easy to predict, and we'll deal with how to tackle the rest. If you want to kind of compare what the Bohr model of the atom was now with the quantum theory, this is a really nice diagram that kind of puts the two together. It does leave a lot of detail out of it, but it does give you some insight into those orbitals. So these are the first four energy levels, which we represent with a letter N, which we'll see more about later today. They're called shells, or you can call them energy levels. Those are more common. And then within each of the energy levels, they're broken into subshells, or you can call them sublevels. So here you can see this down here, this orange blob, which we're coloring in here, that's the nucleus. And as you get further away from the nucleus, you get more energy levels. First energy level has one sublevel. You move further away, there's two. and so on, 3, 4. But as the energy level increases, the distance away from the nucleus increases, and that hasn't changed either. So before we tie in a little bit more about the quantum theory, we're going to go over all of the different orbitals and their shapes and a little bit about them. So if some of this sounds familiar from grade 11, great. If you don't remember a lot, we'll go over everything that you need. So the first orbital shape is an s orbital. It's a spherical shape. Now just for review, when you're looking at these diagrams, they're all trying to show you something in 3 dimensions. So there's 3 axes. So right along here, you've got your z-axis. We'll draw it through for reference. And then there's a y-axis and the x-axis. The y-axis, even though it's here along the diagonal, what it's trying to show is it's coming perpendicular out of the plane of your paper or of the screen that you're watching this on. So it's at 90 degrees. And in all of the diagrams, right at the center of all 3 axes, at your 0, 0, 0 point, this is where your nucleus is located. So if you're thinking about s orbitals and you're thinking about the shape of a sphere and where the nucleus would be, imagine you have something like a hollow ball, like a tennis ball. So the tennis ball is the shape of the s orbital, and the nucleus would be right in the center of that ball in the middle. There's only one type of s orbital, only one spherical shape. This happens in each energy level. And this type of orbital can only hold 2 electrons. So 2 electrons will spend their time within that orbital. If we go on look at p orbitals, they're a little bit different. You've got one on each of the axes, x, y, and z. These ones are sometimes called figure 8 or dumbbell shaped, and they're all perpendicular to one another. If you're comparing an s and a p orbital, s orbitals have less energy, p orbitals are more complex, so they have more energy. 2 electrons can go in each of these. So 2 electrons will spend their time in those orbitals. So if all p orbitals are filled, they will hold 6 electrons. And if you have all 3 of them stacked together on all of the planes, kind of just looks like a 3-dimensional kind of flower or petal, something like that. So there's one on each that are there. The d orbitals and f orbitals start to get more complex. So we don't have a necessarily formal way to describe these ones. Someone say they're like a 4-leaf clover. But then there's one odd guy out here that doesn't look like that. But 4 out of the 5 do have that kind of orientation. And remember, the areas that are here are just regions in space where we're likely to find electrons. So even though the shapes and the orientations start to get more complicated, just think of them as different houses in different locations and different areas, and that's where those electrons spend their time. These are going to be more energetic than the s and the p orbitals. But one thing that's true about them, each of them hold 2 electrons. So 2 in this one, in this one, in this one, this one, and this one. So 2 electrons can go in each. There's 5 of them, so 10 maximum in all 5. As for the f orbitals, they get even more complicated in shape. Remember, even though it looks a little bit more intimidating, just think about it as homes or areas where you're likely to find electrons. These guys appear to have a little bit more space, so they're in a larger size home compared to maybe some of the other orbitals. There are 7 of them here, and just like the others, there's 2 electrons that can go in each of these 7 different orbital shapes, so 14 total in f orbitals. These are the highest energy type of orbital if we're comparing ones in the same energy level. These ones have definitely the most energy. If you recall from last year, the periodic table is also organized by orbitals. and the electrons that occupy those orbitals are found in different regions. In the next lesson, we'll go over electron configurations in more detail, but just as a quick reminder and to tie it in with the orbitals, these are where they're located. The S block over here are your alkali and your alkali earth metals, your first two columns on the periodic table. The D block electrons, the ones that go in the d orbitals, are found in the transition metals, which are in here. Over here you have your P block, your representative elements. So there's some metals here. You have the staircase with the metalloids and some nonmetals. And then down with the F block, you've got your lanthanides and actinides. The only one exception is up here. This is helium, and helium is part of the S block, but we know it's located on the other side of the periodic table, so it's found over there. If we take a look at the periodic table in a little bit more detail, it's also organized by periods, and the periods match some of the energy levels and its organization. So we know the s orbitals start in the first energy level, so it starts at 1 here, and then we can count down 1, 2, 3, 4, 5, 6, 7. There's no 1p orbital. It starts at 2p. So over here we have 2p, then 3p, 4p, 5p, 6p, 7p counting down. There's no 1d or 2d orbital. It starts with 3d orbital. So 3, 4, 5, 6. And the f orbitals start in the fourth energy level, which is why you see it down here, 4f, 5f. There's no 1f, 2f, or 3f. It starts at 4, so we have 4 and 5 for those two rows or periods that are there. So before we tie in some new quantum theory along with the orbitals, let's do a quick summary of our orbitals and their shapes and electrons before we look at some of the theory behind them. So these are our four representative orbital types, SPDF. How many different suborbitals or parts are there to them? There's only one S shape. We have three P's. They're on the X, Y, and Z axes. We've got 5 different shapes for D and 7 different shapes for F. 2 electrons go in each of those types of suborbitals. So 1 times 2 gives us 2 maximum in the S orbitals, 6 in P, 10 in D, and 14 in F. Again, down here, shape just for review, spherical shape, kind of that dumbbell shape, petal or 4-leaf clover, and the F's we'll just call complex to make it easy. Now, we're going to kind of go backwards here. So last year and now, we've just reviewed all of the different orbitals and their shapes. But before their shapes, there was a lot of work that went into figuring out all of these different orbitals, how many there were, um, and the actual diagrams of the orbitals was something that was a lot more recent compared to the background to it. So we're going to try and take a step back and look at where the orbitals came from and look at some of the theory behind them and then connect the orbitals that you're familiar with that background theory. So the 3D orbitals didn't just come out of thin air. There was quite a lot of work that went into them, a lot of complex mathematical equations and theory, and quite a bit of physics. And since there's quite a bit of physics in them and it's higher level physics, we're not covering all of the details of the background in our course. But if you take more chemistry or physics beyond high school, you'll definitely investigate them further. But people that played a big role in those orbitals, we know Bohr. Some of you might know de Broglie, work with waves, Einstein, Heisenberg, and Schrodinger. All of them went into, did some work that went into finding the 3D orbital shapes. According to them, we can't precisely locate an electron around an atom and only predict it. So these orbitals are describing regions where we're going to have a high probability of finding a given electron, generally more than 90 or 95% of the time. A little bit more on a couple of the individuals that came up with the orbitals. These two gentlemen won Nobel Prizes for their work. And again, if you've taken some physics or have a bit more background, you probably have heard of at least one or two of them. So Erwin Schrödinger won his Nobel Prize in 1933, and Werner Heisenberg got his in 1932. And they worked on a couple of different theories involving electrons. So Schrödinger worked on electrons and describing them as waves, and his field of research was called wave mechanics. And Heisenberg was looking at trying to locate an atom, looking at position of electron and momentum. So you can't measure both of those at the same time. Maybe you can find its momentum or velocity. Maybe you can find its position, but to try and do both position and momentum is not known. So that's where his principle is called the Heisenberg uncertainty principle. You can't have the exact position and velocity of an electron at the same time. So that's where the orbitals come into play to show you where an electron might be, but who knows how fast it's going and where it's going next. So now we're going to look at something called quantum numbers. All of these individuals contributed in some way to some of the theory behind the orbitals, and they came up with a small set of simplified formulas and numbers to identify all of the orbitals before they actually came up with their shapes. So mathematically, they could predict how many different types of orbitals there were, how many different sublevels, how many different electrons could fit in them, what are the orientations, and so on, and they call them quantum numbers. So that's what we're going to go over next. So the first quantum number is called the principal quantum number, and we use the letter n to represent that energy level. It's a lowercase n. This tells you the specific energy level and size of an orbital. It has to be a positive whole number, so it starts at 1 and goes 2, 3, 4, and so on. So this number will always be a whole number and a positive number, not 0. Um, you can also use this number to figure out how many electrons can be held in a particular type of orbital. Um, in any energy level. So if you want a little cheat or a shortcut to find out how many electrons are in a given energy level for an orbital, it's 2n squared. Take that energy level, square it, and then double it, multiply it by 2. The next energy level is called the secondary quantum number. Now we use a lowercase l for it. So I've got it here in a different font, but it's often easier just to use a cursive L. That's very commonly used, just so you don't mix up the number 1 and a lowercase l, because they look very similar, especially when you're typing it out. The secondary quantum number describes an orbital's shape. This has values anywhere from a range of 0 up to n minus 1. Remember, n is the principal quantum number. So n minus 1 means take the energy level and subtract 1. These also have to be whole numbers here. They will also only be positive, but in this case you will get one where there is 0. So here are the 4 different secondary quantum numbers. They calculated 4 of them, and coincidentally there are 4 orbital shapes. They'd figured out the letters and shapes of them later on, but using the secondary quantum number, they figured out these are the 4 values that we can have, and then therefore these are the 4 shapes that are most commonly seen. So when L is equal to 0, it means you have an S shape. When L is equal to 1, you have P shape. When L is equal to 2, you have D shape. And when L is equal to 3, you have an F shape. So how does this all tie in with the formula and the principal quantum number? We're going to work through a couple of them together. So if n is equal to 1, if we wanted to find out how many orbitals there are in the first energy level, we know it should just be 1s. There should only be one of them. But if I want to use one of these formulas, what do I do? So remember the formula here is 0 all the way to n minus 1. That's what we want to try and calculate. So let's do that for each of these here. So if n is equal to 1, I'm going to have values all the way from 0 to 1 minus 1, which means 0. So in this case, that means L can only be 0. I'm only getting one number. When L is equal to 0, we said that this is going to be an S shape. So we know in the first energy level, there's only the S orbital because I only end up with one L value. If we try it for n equal to 2, 0 all the way to 2 minus 1. So now this means I'm going to include 0 and 1. So here my L values are 0 and 1. What does that mean? I've got an S orbital for the 0 value, and the 1 value is representing P. So in the second energy level, I have 2S and 2P. If I do it for n equal to 3, 0 all the way to 3 minus 1. So I'm going to get 0, 1, and 2. So that means here my L values are 0, 1, and 2. So again, 0 always means S, 1 means P, 2 means D. And if we think, well, what can I find in the third energy level? I know there's 3S, 3P, and 3D. So that's why I get 3 numbers here. They knew 3 different types of shapes and then figured out what the shapes look like later on. And we can keep going, do one more for 4. So hopefully you see the pattern now, 0 to 4 minus 1. This will give me 0, 1, 2, and 3. So that means for my L values, I've got 0, 1, 2, 3. This is going to mean S, P, D, and F. There are 4 in the fourth energy level. The next quantum number is called the magnetic quantum number. It describes the number of suborbitals. Again, we're using the L, so if you're writing it on paper, M with an L lowercase cursive L, often put as a subscript there. So remember, suborbitals mean how many different types of houses within that orbital. So for example, the p orbital, there are 3 different p orbitals, one on X, one on Y, one on Z. So there's 3 suborbitals for p. So that's what we're talking about here with this number. How do you find out what the range of values are? They go from negative L all the way up to positive L. We count by ones or integers here, no decimal places or fractions, always whole numbers. So we're going to do the same thing again. We'll walk through each of these ones so you can see how this works. S orbital we know has an L value of 0. So if I'm trying to find the ML value, it's going to be negative L all the way to positive L. But you can't have negative or positive 0, it's just 0. So in this case, ML is equal to just 0. It has one value, and one value means only one type of suborbital. And that one suborbital has to be S. So we know only one S orbital. We get one value generated for ML. Here the number doesn't matter, we're just looking at for how many values are generated. Next, let's tie it in with P. So L is equal to 1. That means ML is going to be negative 1 all the way to positive 1. So here, my ML will be negative 1, 0, positive 1. So here I've got 1, 2, 3 values for my ML. 3 values for 3 suborbitals. How many different p orbitals are there? X, Y, Z. One of these is X, one of these is Y, one of these is Z. We go back now to d orbital. Again, hopefully you're starting to see the pattern. It goes from -2 all the way to +2. So that means my ML values are going to be -2, -1, 0, +1, and +2. 1, 2, 3, 4, 5. 5 values, 5 suborbitals. How many different shapes of d orbitals do you have? There are 5 of them. And finally, f orbitals, ML will be from -3 to +3. So -3, then we want to do -2, -1, 0, 1, 2, 3. When we count these up, 1, 2, 3, 4, 5, 6, 7. 7 values, 7 suborbitals. How many different shapes of f orbitals do we have? There are 7. Before we go on and look at the last quantum number, let's try and take what we've learned about our L values, our secondary quantum numbers, and ML values, and tie them back in with what we learned about the orbital shapes. So in our notes, let's flip all the way back to our diagrams of the 4 orbitals. And if you have a different color, that's something to write with your notes, this would be a good time to use it. So for an s orbital, the secondary quantum number, or L value, we said was 0. The ML value here, we also just stated was 0. So to indicate that you have an s orbital, that's where the L value is equal to 0. And the ML equal to 0, 1 value here, tells us you only have one suborbital or one shape. If we do the same thing for p orbital we know is L is equal to 1. When I see L equal to 1, it's telling me I have p orbital. There were 3 ML values. ML equal to -1, ML equal to 0, and ML equal to +1. 3 different suborbitals. Each value is assigned to a specific orbital orientation. So we've got ML equal to -1, 0, and 1 for each one of those 3 p orbitals. For the d orbitals, this is when L is equal to 2. That tells you have a d orbital. And again, ML values are going to go from -2 to +2. So this one's ML equal to -2, -1, 0, +1, +2. 5 different values correspond to the 5 different suborbitals. Lastly, you've got the f orbitals. This was L is equal to 3. ML values go from -3 to +3. -3, -2, -1, 0, 1, 2, 3. 7 different values for 7 different orbitals. So hopefully that helps tie in a little bit of the orbital shapes you might be a little more familiar with some of the simplified quantum numbers and their formulas. Remember, the quantum numbers came first, and the actual 3D rendering of the orbital shapes came later. So now let's go back to our last quantum number, which is called the spin quantum number, which is called MS. This one tells you the direction in which the electrons are spinning. We're going to see more application of this number in the next lesson. The two possible values for ms are either positive 1/2 or negative 1/2, which mean an electron is spinning up or down. When we do some diagrams in the next lesson, we show these with little half arrows. So a spin up will look like a half arrow pointing up, and a spin down will be a half arrow pointing down. So let's make sure you can try out a couple of problems before you try some out on your own. So if you want to give these three questions a shot, then you'll be able to see if you're starting to get the idea of how to use some of these quantum numbers. There's lots of different ways and questions that can be asked of you, so hopefully these three will help you get started. So I would pause the video now, try them out, and when you're ready to take a look, unpause and I'll walk through the three answers with you. So here's the answer to question number 1. Determine the greatest number of electrons that are possible in the first 4 energy levels. The easiest way to do this is use your little formula that we introduced with the principal quantum number. If I want to know the maximum number of electrons in all of the energy levels, I can use this really quickly to do that. It's not the only way you could answer this question, but it's a fast one. So we'll walk through this and then I'll show you the other way that you could do it. So take your energy level 1, square it, and then multiply it by 2. In the first energy level, you get 2 electrons. In the second, you get 8. And the third, you get 18. In the fourth, you get 32. Now, if you remember a little bit about your electron configurations from last year, you may have done this a different way. The first energy level has 2 electrons. That's all there is in there, 2. Second energy level, 2s2, 2p6. 2, 6 is 8. 3s2, 3p6, 3d10. 2 plus 6 is 8, plus 10 is 18. 4s2, 4p6, 4d10, 4f14. If all of those orbitals are filled within that energy level, 2 plus 6 is 8, plus 10 is 18, plus 14 is 32. Add those all up, you get 60. Maximum 60 in the first 4 energy levels. Okay, again, if you haven't tried the next questions, pause now, try them out, and you'll see the answers next. All right, so the second question was, if n is equal to 3, what are the allowed values for L and ML, and what does this mean? So if n is equal to 3, that means third energy level. So your L values can be from n minus 1 down to 0. So that means you're going to have an L value equal to 2, which is D, L value equal to 1, which is P, and an L value equal to 0, which is S. So you've got a D, a P, and an S orbital. 3D, 3P, 3S. So those are the allowed L values. Now, what are the ML values? That depends on the L value that's associated with it. So if L is equal to 2, your ML values will be, remember, negative L to positive L. So negative 2, negative 1, 0, 1, 2. If L is equal to 2, you will have 5 different ML values. If L is equal to 1, we go from negative 1 to positive 1, which means 3 suborbitals. And if L is equal to 0, we know ML is only equal to 0, so 1 suborbital. Last question, make sure that you've tried it. Here's your answer. So what type of orbital is designated by these quantum numbers? So n equal to 4 tells you have the 4th energy level. So that's this number here. L is equal to 2 tells you have a d orbital. So we've got a letter, 4th energy level, and a d orbital. So a 4d. And since there is only one value here, it doesn't mean that there can't be more ml values. It just means we've only stated one ml value. It's going to only represent one of the d orbitals. You're not expected to know each of the individual orientations, and there's notations with them. We don't need to be bothered with that at our level of chemistry, but it'll just represent one of those orbitals. So to answer this question, you have one of the four d orbitals. So make sure you get lots of practice. There's a few different good worksheets with a variety of questions, and this will help tie in some of the background quantum theory to the orbitals that you may already be familiar with.